Welcome back to Nick Does Maths. Let's solve some simultaneous differential equations. Now we have here a pair of two linked first order differential equations that we need to solve. Getting a sense of deja vu here. Did I do this one? I think I did. Well, look, I'm going to show it to you in a different way using matrices, eigenvalues, and eigenvectors. What am I on about? Buckle up, buckaroo. Right, first things first, let's rearrange this a little bit to get dx by dt is minus 2x plus 4y, and we're going to get dy by dt is equal to minus 3x plus 5y. Now, the cool thing about this is I could write this as d by dt of xy is equal to minus 2, 4, minus 3, 5 times xy. Now, why might that be useful to me? Well, I'm going to try this idea. What if the vector xy, now they are linked, right? So it kind of makes sense to me that maybe this is some vector times e to the lambda t. Okay, so the point is I could have x is some numbers of e to the lambda t and y is some number e to the lambda t, right? V is just going to be something a, b, something like that. And we're going to do that because they are linked, all right? So if x grows or decays as e to the lambda t, it makes sense that y does the same thing. But if I plug that in, if I differentiate that, I get lambda v e to the lambda t is equal to minus 2 minus 3, 4, 5 times v times e to the lambda t. E to the lambda t is just some scalar, so we can pull it out front. But what might we notice here? We might notice that all this means is lambda needs to be an eigenvector, eigenvalue of this matrix, and v needs to be the corresponding eigenvector. So, minus 2 minus lambda, 4 minus 3, 5 minus lambda is 0. Bosh, bosh. Plus 12 is 0, which gives me lambda squared minus 5 lambda plus 2 lambda minus 3 lambda plus 2 is 0. That gives me lambda is 1, lambda is 2. If you watch my previous video, this should ring a bell. Now let's take the corresponding eigenvectors. If lambda is 1, all right, where should I do this? Let's take lambda is 1 over here. We're going to take v is, I don't know, uv. So uv has to equal to minus 2u plus 4v minus 3u plus 5v, that side over there, which tells me that 3u has to equal to 4v, and I think that's the case in both of them. So I will take my vector. Now, the important thing is my vector in this case is then some multiple, because you can always scale this up, of the vector for 3. If we go for that one, then we go lambda is 2. We go lambda is 2. So we get 2u is minus 2u plus 4v, and we'll get 2v is minus 3u plus 5v. In both cases, we get u is equal to v. So the vector is going to be some multiple of 1, 1. So what that tells me is xy is some multiple times 4, 3 e to the t plus some multiple of 1, 1, e to the 2t. And now we can plug in my initial conditions. When t is 0, x is 0, y is 1, 0, 1 is equal to a times 4/3 plus b times 1, 1. And we solve that. We solve that. Do this line minus that line. Minus 1 is a, which tells me that b is 4. So altogether, that gives me the solution. Ooh. Xy is minus 4 minus 3 e to the t plus 4, 4 e to the 2t. Isn't that cool? Isn't that cool, right? Instead of solving all the stuff for x and then plug it into y like we did last time, instead, we've got this really cool way of dealing with xy as its own vector all the way through. So we're basically solving for x and y all the way through. I just think it's really neat. Now, bear in mind, this only really works because I can express it in this way, all right? If you start having functions of t on the right-hand side, this ain't going to work. It doesn't really work, but it's a really cool way of dealing with it in some cases, and it has really nice applications later on when we start looking at nonlinear ones of those at undergrad level. There you go. Same question, two ways of doing it. What do you know? Don't forget to like and subscribe so you don't miss the next one of these. Am I going to come up with a third way to solve this? Maybe. I'm Nick. I'll see you next time.